Thank you, Steve. Thanks again. I really should thank Steve to give me a chance to talk about the two topics that actually get me in an excited state. The first topic is my research, and the second topic is the Department of Chemical Engineering. What I'd like to do is just give you an overview of what's going on in the Department of Chemical Engineering. There's actually a sea change in the department. There's no better representation of that sea change than this figure right here, which is our new building. On a normal day in California, I wouldn't have to put this slide up there because you could see it quite clearly. But actually, it's a cloudy day, and the curtains. There is what we call Building 4 up to this point. That is the new chemical engineering and bioengineering building. This is what it looked like. I have actually a much more interesting slide later, which is a time-lapsed video of the construction of that. This is the artist's depiction of what it was going to look like when we a couple of years ago. So this is a huge change for us. It's a huge change for us, not just in terms of individual PIs, labs, but labs for teaching, conference rooms, classrooms, etc. And it is coupled with a very big change in our department, both from the point of view of personnel, that is to say we're growing and hiring, and with those changes come a change in kind of our direction and focus. So I'm going to talk a little bit about that. Oh, and I'm going to do it with the right computer here. Okay, all right. So this is us right now, 14 strong. This is in alphabetical order. We are, at this point, 5 untenured faculty, which is a large fraction for 14. And these people, almost to a person, are all engaged in some kind of aspect of materials research. I'm not going to try to cover all of them. I'm going to cover a select few. But a couple of years ago, now almost 2.5 years ago, we got together and said, hey, we're entering this period of time where we're moving into a new building. We've been given the authorization from the powers that be, meaning the dean, to grow to somewhere around 18. We really need to plan this because we've gone from what I would call a small applied science department that was actually an outcropping of chemistry, where we were for years and years about 8 faculty, to now something that's 14 moving to 18. And so that's a very large change, and so we needed some plans. So we developed kind of a different way of looking at ourselves. This is something from our youngest faculty member who decided to throw us on this triangle because the 3 areas, the 3 topics, if you will, that cover our whole ability, our intellectual breadth, is biology, physics, and chemistry. And we're somewhat scattered on this triangle in terms of what our abilities and skills are, but we all focus on something called molecular engineering, and I think this is something we rally around, that we're interested in engineering at the molecular scale. And all of us do that, and we apply our different skills to that engineering. And I talked about ours in the beginning. What I do in my group is try to molecularly engineer fluids, but there's a variety of that. So this is the way we used to think about ourselves. This is more along the lines of characterizing ourselves with a skill set, transport and soft materials. You heard about that earlier. Catalysis and surface science and bioengineering. We do, and I think all good chemical engineering departments have an aspect of biological engineering in their department. We still do, even though there's a bioengineering department. We'd actually do quite different things than the bioengineering department. For example, we have bioenergy going on in our department. But you notice that this characterization still leaves us scattered. We now characterize ourselves this way, which is the chemistry of life, chemistry of energy, and chemistry of the environment. So when you go to topical descriptions of what we do, you see it brought us together, because all of us have projects that are engaged with life, energy, and the environment. So chemistry of life, what we're referring to is human health, the creation of medicines, materials for therapies, etc. Energy is kind of obvious for this crowd. Environment for us means sustainability, sustainable green processes, etc. Again, sorry. It's amazing how I need to notify myself of everything, and then I still am late. Okay. So anyway, this is how we characterize ourselves now, and it has brought us together from a department that in some sense is disparate in their skill set to something that is quite unified in terms of their topical areas. The other way we think about ourselves is building bridges, and I made this slide up a couple of years ago and was kind of amazed. I decided to essentially put down all of the entities on campus in which we had collaborative research or collaborative educational opportunities. And it's quite remarkable. School of Engineering, School of Medicine, SLAC, H&S, and the School of Earth Sciences, all of us have connections to them in terms of shared students, co-advised students, etc., joint grants. The largest connection actually is to the School of Medicine. More than half of our faculty are actually engaged in creating new medicines, creating new diagnostic tools, etc. But the fastest growing area, I would say, is in the energy area. But the energy activities are actually spread through the School of Engineering, the School of Earth Sciences. So the fastest growing is over here, but the one that is essentially floating the boat right now is our connections to the School of Medicine. We also have a 5-year plan. It's about 2.5 years old. This again was created in lieu of the fact that we were coming into a new building and had a growth plan. So we wanted to develop this. And this is a real nuts and bolts kind of 5-year plan. Not many motherhood statements here. It's actually what we plan on doing to change the department and the department culture as we move into the new building. And so one of the things, some of you might have come to these get-togethers with the EAP in previous years. You've heard some of this. We have essentially a chemical energy conversion center within the department. It's joint with SLAC. It's called SunCat. The director is Jens Norskov. Our design here is to build this and grow. Jens is a professor in chemical engineering, and we're growing this as a joint project between SLAC and ChemE. And when I say grow, it means hire faculty, essentially create graduate student communities that are joint between SLAC and ChemE, and if you will, mirror the kind of situation that Berkeley already has between Lawrence Berkeley Laboratories and their chemical engineering department. We have been given the go-ahead to do at least 3 incremental hires in 5 years. This has been modified a little bit because there are some new things which I'll mention. But now when we talk about where we want to go, we think in terms of building those bridges that I talked about a little bit earlier. So we've written down a bunch of areas where we think growth in chemical engineering is the future, and this is where we want to be. We're still a best athlete department, so we have broad searches and we hire the best athlete. But if one of those athletes works in this area, we're happy as a clam. So this is in our 5-year plan. The other thing is we are about half of our undergraduates come to us now and say they want to work in energy. That is to say they want to do energy research over the time in which they're undergraduates. And another half of those people are actually part of our coterm program, which is essentially a +1 year on our undergraduate program. They do coterm masters in a variety of different departments on campus, but again, half of those people want to do something which focuses their research on energy. So we now are increasing our energy options within the undergraduate program, and we do that in a couple ways, and I'll mention that. Our graduate program is actually extremely healthy. I would say we are the primary competition, if you will, with the school that will not be mentioned, which is MIT. And because there's a large sucking sound of American graduate students into MIT because their parents want to go. But we compete actually quite well with American graduate students with MIT. As you see, our return in 2012 was 65%, which is actually quite good. We're a much smaller shop than MIT, but nevertheless, we compete with them very well. And then the other part of this, our 4th rung, if you will, of the 5-year plan, is new corporate relationships and invigorated alumni relationships. And we've actually hired an outreach administrator, a full-time person called Sandra Handy, and Sandra Handy's actually in the back. And she organizes in a very efficient way our outreach to companies as well as our website, etc. So she manages this in a way that has never been done before and is reaping tremendous benefits. So let me talk a little bit about this, what was a hole in the ground and now is that thing you can barely see through the curtains over here. I want to show you, I won't just show you the artist's depiction, because if you squint you can see it. I'll show you this. This is pretty interesting. I've had this at receptions for chemical engineering. This is what happens over a relatively short period of time, a 2-year period of time. As you see, we go from a hole in the ground to what's behind me. And it's pretty interesting because the last part is the fastest growing palm trees you've ever seen in your life. They're coming. No. They're right here. They're coming. There they go. All right. Fine. So, so what you have to understand is our excitement about this is we haven't been in the same building for 50 years as a department. In fact, we live right now in 4 different buildings. This is the first time in 50 years the Department of Chemical Engineering will all be in the same building and in world-class facilities. So this is the some of the motivation for the changes that we're making. Probably the most exciting part of that building for us is right here. This is the first floor. The first floor has no PI labs on it, but it has this enormous section of teaching labs. And this is fantastically interesting for us because our undergraduate program is growing for the reasons that I gave, because most of them want to do energy research. And we now have state-of-the-art facilities to do teaching labs. And we have a broad array of lab courses for the undergraduates that we're housing in here. The other thing is this stadium seating course classroom, which is great for us. But I wanted to emphasize the teaching laboratories. So I want to walk a little bit through our 5-year plan and tell you some highlights from it. Again, I talked to you a little bit about SunCat. SunCat is this bridge between SLAC and ChemE that lives at the intersection between those. It also lives on this thing called the energy spectrum. If you've never heard Lynn Orr speak about the energy spectrum, that is the spectrum of activities associated with energy on campus, here it is. And a lot of it is heavy on the policy side, and we're all the way down here at the basic science side. So the basic science side is less populated, and that's where SunCat lives. SunCat lives in the molecular engineering of energy technologies. So anything that involves molecular transformations that are associated with energy storage or energy use is where SunCat lives. And the focus there is on catalytic activity, but it can involve non-catalytic processes as well. And that's what SunCat is. So essentially it has associated with it synthesis, characterization, theory, and application. And there's a materials aspect. Obviously, catalytic materials is part of this. It fits in our chemistry of energy theme. And there's a number of major activities, major problems that are already being looked at: syngas conversion, battery chemistries, electrochemical N2 ammonia synthesis reduction, etc. Why are we the people to do it? Well, we're the people to do it for a number of reasons. First of all, we're taking advantage of this world-class facility, SLAC, which is sitting here. And if you look at the comparison at LBL and Berkeley, there's 250 chemical science students that are supported by LBL. That number at Stanford has been very small until the last year, and now we're up to about 30. Going up. So we're taking advantage of a world-class facility now. It's having an impact at Stanford. So that's one reason to do this. The other reason to do it is that we have more than half of our faculty in chemical engineering that are involved in some kind of energy research. As you see here, there's a whole spectrum: photo and electrocatalysis, advanced synthesis, inorganic materials for solar conversion, biological fuel cells, plant biofuels, sustainable production, and the theory for fuel cells is associated with it. So we already had a whole host of our faculty involved in energy. It was important to mine that in a very significant way. Now, things have happened since we have our 5-year plan, and I should mention those to you. There's now an Institute for Chemical Biology, which is Chetan Khosla, who's one of our faculty members, is the director of, and that's associated with hiring faculty and focused on molecular engineering of drugs. So the chemical engineering department's, of course, not just interested in the molecular engineering of energy, but the molecular engineering of pharmaceuticals, and that's particularly part of our chemistry of life. And we now have an institute that's associated with that and associated faculty members. So that's something that has happened and we're focusing on. There's also this Makers Commons. You might have heard about this, which is part of a materials initiative that's going on campus. And Jens Norskov is a big mover and shaker in that, so we're associated with that. Again, the other thing that's happening is we're being thrown into that building, and as a result, we're building ties with bioengineering because we're now occupying, in some sense, the same space. And we have shared laboratories, et cetera, with bioengineering. Bioengineering grew up essentially external to chemical engineering. They've actually hired chemical engineers from other faculties. And so we're developing further relationships with them as we move into the new building. To do that, you know, the university gives us this great building, but they actually don't give us the equipment to go into it. So we have a fundraising campaign called Engineering Our Future Fund, and we're essentially bringing alums together to raise money to hire new faculty and to essentially staff the building with technicians, as well as put new equipment in those teaching labs. The MEET program is an outcropping of our new energy, essentially, activity that's associated with SunCat. This is a professional development program. So we have a graduate certificate that industrial people can take online. It's a series of courses. As you see here, there are 6 courses. You have to take 4 to get the certificate. This has now been on the books for more than a year, and we have quite a number of industrial people that are signed up and taking these courses. And it spans the range all the way from microbial bioenergy all the way to actually entrepreneurship in energy companies. So it's quite broad, including heterogeneous catalysis, environment, electrochemistry, etc. And this has been very successful for us and is a new certificate within the School of Engineering. It's actually, we've brought back a number of lecturers that are not Stanford faculty per se, but are lecturers, alums that have a lot of industrial experience, Howie Rosen and Ricardo Levy here, to, for example, teach in our entrepreneurship section. So this has been a rallying point, if you will, for alums as well within our department. I will now mention, probably in a much poorer way than they could do it, a number of research projects that are going on in the chemical engineering department, just to indicate the kind of breadth of materials research that's going on within our department. You've already heard about the fracking stuff, which I talked about this morning. The fuel cell, obviously, design is something that you all know about and has important materials applications. One of the ideas is to operate in both fuel cell mode and storage mode. So to have a single device which works in electrolysis mode and fuel cell mode. So produce the H2 in the daylight, but then use it at night would be the idea. Now, that's a materials headache from a number of points of view. You need a catalyst, essentially, on the H2 production side, and you need a membrane, essentially, that's permeable to on both sides of the operation of this device. And Kurt Frank, who's sitting in the back, works on one of the aspects of this, which is novel polymer design for the membrane. This is a polysulfone design for this hybrid device. And Tom Jaramillo works on the catalyst side of things. In this particular case, we're looking for a catalyst for hydrogen production, and earth-abundant catalysts are cheap and the best way to go. And in this case, molybdenum sulfide turns out to be a good catalyst, not the best catalyst, but a very cheap, excellent catalyst. And he engineers this catalyst by creating steps. It turns out steps and facets in these things are the most catalytically active. And so he has a project in his group that looks at molybdenum sulfide nanoparticles. It goes all the way from, and Steve's standing next to me, so he wants me to sit down. It goes all the way from solar cells that are developed through ALD by Stacy Bent to electronic skin. So here's sensitized skin, organic electronic skin, which has built within it sensors that can produce an electric current when this skin is touched. And that's the work of Zhen and Bao. And then finally, I just wanted to say about our newest faculty member. She's actually a biochemist by training, but works on both life and energy. So she makes plants that are more resistant to disease. They produce their own antibiotic. And she also does delignification for the use of biomass as bioenergy. So she's on both sides of the life and energy. And we're very, very proud that we can have somebody who sits on both sides of that equation in our department. Okay, so let me finish with this slide just to remind you what our three themes are, and then it's brought us together around life, energy, and environment. I'd be happy to answer any questions. Thank you.
Thank you, Eric.